Hey folks, this is Major Jones here to talk to you about time parameters. So in this lesson we are going to peel back the layer once again on our digital circuits to realize that timing is really important to some of their operation, and we're going to identify in what ways those affect our circuits and what are some solutions. To start with, we have kind of three revelations for you about how these circuits work in real life. All right, so number one, imagine if you would trying to move a really heavy box. Even if you were a very strong person, even if you had a bulldozer, this box is not going to move instantaneously, right? It might move fast if you have a really big piece of heavy machinery, but it's not going to be immediate. And similarly, electrons have mass. It's really tiny. It's a really small amount of mass, but it's mass nonetheless. And so electrons themselves also do not move instantaneously, which means we've been drawing our waveforms kind of idealized this whole time with, these nice straight edges, instantaneous transitions from 1 to 0 or 0 to 1 on our logic signals. And that's not entirely correct. You can see here a signal, digital signal A. In reality, it takes sort of some amount of time to go from one logic level to the other. For the sake of just simplicity, what we say is that it's the point where it sort of crosses that exact 50% line between the 0 and 1 that the signal actually changes. And so you'll see sometimes on these diagrams a little horizontal line right in that slanted portion to indicate that that's where, for simplicity's sake, the logic signal changes from a 1 to a 0 or back and forth. Right? So that's revelation number one. Signals don't change instantaneously. Number two, imagine, if you would, having a phone call with someone who is really, really far away, right? Like maybe you've had a phone call with someone who is on the other side of the continent, or even, in Asia or Europe, like around the world. In that phone call, you may have noticed that there was some lag between, what you were saying and what was finally received on the other, person's phone. There's a delay that from when you spoke something to when it sort of came out their receiver. And so similarly, gates have a delay from when an input signal changes to when the output reflects that signal. So you can see here on the right-hand side, I've got a simple AND gate. My input, one of my inputs is changing from low to a high, so the output of the AND gate should go high now, so both inputs are true. But there's a non-zero length of time that it takes for the output to reflect that change on the inputs. And it's kind of similar to this idea of, having a long distance phone call and speaking something and needing to wait some amount of time before it sort of comes out the other end. Of course, just like our signals over here, right? This is still really fast, but it's non-zero nonetheless, and it matters in certain circuits. So this is this amount of time that it takes for an output to reflect a change on the inputs is called the propagation delay. Right? So that's revelation number two. Signals take some amount of time to get through a gate, and that's called propagation delay. Number three, let's imagine a D flip-flop, if you will. And we're going to give a rising clock edge to this D flip-flop to be able to sort of clock in new data. And the one kind of hiccup with this setup is that I'm going to make my D input transition at exactly the same time as my clock. They're identical. So bear with me, if you will, with this thought experiment, right? If D transitions at exactly the same time as the clock, what goes to our output? And kind of, if you're thinking about this, the answer is really like, we don't know, right? Like there's, the exact value of D when the clock sort of goes from a low to a high is anyone's guess if it's really truly exactly at the same time. So what we can probably conclude from this is, okay, well that sounds like a bad idea, right? Let's make sure that the D input isn't changing at exactly the same moment as the clock signal. And honestly, though, we could probably extrapolate that. We could say, well, okay, it's not even necessarily the exact moment in time that we care about. There's sort of a window, right? So up here you can see that it would behoove us to make sure that there is some window of time, both slightly before and slightly after the clock is transitioning on a flip-flop, when the inputs should not be able to change. Because if they do within that window, then it's close enough to the clock edge that weird stuff might happen to the D flip-flop. Or maybe it's just more accurate to say that we just really don't know what's going to happen to the output because the input signal is transitioning too quickly. So the window that we want to keep our inputs stable prior to the clock edge is called the setup time. And the window that we need to kind of hold those signals stable after the clock edge is called the hold time, right? So this imposes a bit of a little restriction right around the edge of our clock if we want to make sure our flip-flops operate correctly. That's revelation number 3, right? And as we'll see, these 3 revelations, they impact our circuits in a couple of ways. Let's make we'll make a slight diversion. I'll show you in just a minute kind of how these 3 revelations change the way we might design our circuits. Let's take a little diversion into the world of really fast signals to kind of warm our brains up for thinking about our digital logic circuits and how these 3 revelations sort of change the way we design them. So let's take a very simple circuit, right? This is, in fact, it's so simple it's a wire, right? I've got a slide switch here, right? One of those slide switches that are on the digital trainer, connected via a wire to an LED. And internally, right, this slide switch is in one position connecting to positive voltage, and in the other position it's connected to ground. And so the LED is just going to show, the position of this switch, basically. Well, it turns out that this slide switch is actually inadvertently a fast signal, all right? Because what happens mechanically when I move this slide switch to one position or the other is that I'm moving a piece of metal from one contact to another. And the piece of metal that's making this contact, let's say I'm moving it from a high to a low. When it connects to that ground contact, it doesn't just sort of, attach and rest itself there. Mechanically what happens is that there's some bounce. When I move that slide switch down, the middle contact sort of ricochets off of that ground contact, that zero contact, a couple of times before it settles out. You can see that in the graph here, right? The top position is the position of our switch, and you can see that it's sort of ricocheting off of that closed position. And the result is that the output kind of goes back and forth between a 1 and a 0 really quickly. And in the case of this circuit up here, if the result of this circuit is my LED, and I'm looking at it, the ricochet happens so fast that I don't see it. So honestly, this circuit's totally fine. But it comes out, it's a result of the fact that even though I have a very fast input signal, my thing that I'm using it to sort of drive my output, if you will, is responds relatively slowly, right? That's a key distinction. We'll see circuits in the future where the output responds relatively quickly, and then this switch bounce, this really inadvertently fast signal, becomes a problem. In fact, let's look at that right now. Okay, so let's make one little change to this circuit here. Instead of driving an LED, I'm going to use this switch to drive the clock signal for a D flip-flop. Or alternatively, maybe I'm using an Arduino to read that position of that switch, and that switch is connected to an interrupt, which will respond instantaneously when the level changes. Or alternatively, maybe I'm reading this switch really fast. Or consider a third scenario, right, where I'm using this switch as the input to a finite state machine. Only the finite state machine has a really fast clock. It's looking, it's making transitions thousands or hundreds of thousands or millions of times a second. And all of a sudden, what should be a clean 1 and a 0 on my switch is not. And what happens in these cases are these outputs will respond to each one of those level changes, right? The clock here, when I press my switch, if I intend for this to be sort of one clock cycle on the bottom here from a 1 to a 0, but there's multiple switch bounces as it goes from a high to a low, that D flip-flop's going to see, like 3 or 4 more clock edges, all right? Some of you actually may have realized this if we were playing around with the D flip-flops or the counters. If you tried to wire up your clock to like one of your switches, kind of random stuff started happening because the bounce caused the flip-flop or the counter to see multiple clock edges. So this is a general problem called switch bounce that we need to take care of. The strategies we're going to use to take care of it are called debouncing strategies. All right, so I'll show you a couple real quick, and then we'll move on to some other circuits. So number one, we can slow it down, right? We can try to slow down the signal coming from that switch, and so that it sort of smooths out those transitions. So one way we can do it is in hardware. We can use a resistor and a capacitor connected like this to my switch, as basically a low pass filter. Right? This capacitor is going to sort of charge up the same way it did for our like 555 timers. It's going to charge up and charge down kind of slowly through this resistor. And so I can sort of use that to kind of help smooth out the edges of my bounce. And then lastly, I'm going to send that into something called a Schmitt trigger. Right? I included the graphic here because I'm no good probably at drawing this little internal diagram. This little symbol in the middle that looks like a kind of a weird O with a hat and a tail is reflective of the little transfer function for the Schmitt trigger. So the Schmitt trigger has what's called hysteresis. And that means that there's sort of like a high and low threshold. So you can see here down at the bottom of this graph, I have my input voltage, how that corresponds to my output voltage on the vertical axes. And you'll notice that there's this middle area here where if my input was low to begin with, right? If I started all the way on the right-hand side of this graph and then moved my way into this middle section, the output, my vertical bar, stays low until my input goes below some low threshold, right? Once it's below here, it looks like 0.9 volts, right? That's when my output inverts, and I'm here. I'm at my high output. And once I'm here, if I'm at my high output, right, I don't fall back down until I exceed my high threshold, which you'll notice is sort of like past this little middle region. And so this is very much like our 555, right? Like the output was only set and reset if I were like above and below, like 1/3, 2/3 VCC. This is sort of that same operation, and what this does here is it helps take the signal that we're smoothing out, and even if it bounces a little bit as the capacitor is kind of charging and discharging while that switch is connecting and disconnecting, it makes sure that once this signal sort of falls below like this high threshold. Once it's the low threshold. Once it's below the low threshold, it won't come back up until it's above the high threshold, and that is very unlikely to happen unless the switch is actually connecting to power, unless it's in the actually in the other position. Right? So we can use a resistor, a capacitor, and a Schmitt trigger to kind of slow down our input signal. We can also sort of do that in software. So here's a little example of trying to read the button in software. And a very simple debouncing strategy for software is to sort of read the button, wait 20 milliseconds, and then check the value of the button again. If it's different, then it might be bouncing, and so we'll not do anything. But as long as it's the same, then there have been 20 milliseconds where this is that the output has been sort of consistent. And so if that's the case, then we'll say, okay, we can update our button value in software with sort of whatever the latest reading was. And there are much more complicated strategies to debounce in software, but this is one such. All right, so option A, if we've got a switch that we need to debounce, is to slow it down. Option B is to just change the circuit slightly. So you'll see here I'm changing, instead of a slide switch, I'm using what's called a single pole double throw switch. This is like the push buttons on the digital trainer. So one end of my switch, the centerpiece is connected to ground. The other end of my switch are connected to an SR latch, each with sort of a pull-up resistor. And so what this does is that the switch is not necessarily bouncing back and forth between each terminal, right? It's if I move this switch to the bottom position here, then all it's doing is sort of touching and then letting go, and then touching and then letting go on this bottom contact. And so in this circuit here, right, if the switch is in the top position, then my set is low and my reset is pulled high. So I'm resetting my output, right? So this would be like the low position. As soon as I let the switch go, and actually, sorry, these should be pull down resistors. Sorry, because I forgot that in our SR latch, right? They're both active high. So forgive me. These should be connected to ground. In which case, if this is here, S is connected to, and this should be connected to power. So I'll release an updated diagram of this in a second. But the idea is that I'm alternately setting or resetting my latch based on the position of the switch, and the fact that it bounces a little bit on each of the contacts is fine, because when the switch, the metal piece sort of bounces away from a contact, the SR latch is just sort of in the hold position. All right. So this is another really common way, kind of certainly in hardware, to debounce a switch, and I'll post an updated diagram of this in after I record this. Okay, so those are some of the problems we see from really fast signals, especially when they're feeding into things that respond very quickly, like the clock input to a D flip flop, or like the interrupt pin on an Arduino. All right, so let's take a look at another circuit. Now this time we do need to worry about our propagation delay, and again we'll see sort of two instances: one where it's fine, one where it's not. So here I've got the sample circuit from the notes. I've got an ABC input that are going through these gates to, let's say, a motor, right? So the output of the circuit is kind of driving a motor. A motor is going to respond very slowly. It has mass and inertia, and so even though like you read in the notes, there is a little glitch on the output when I transition from this box in my KMAP to this box. This circuit's totally fine, right? That glitch is small enough that the motor's not going to respond to it, and this circuit is totally okay. But we have a problem again when we're using the circuit to drive something that responds fast, like the clock input to a D flip-flop. All right? When B, and specifically when A is low, B is high, and C is high, my output is high. All right? So A is low, B is high, C is high. When I'm in this box, my output is high. When B goes low, right? B goes from a 1 to a 0. The input to this AND gate changes faster than the input to this AND gate because of the propagation delay of this little inverter, which means this gate itself turns off, right? B goes to a 0, so this gate goes low before this gate can turn on, right? It'll turn on when the 0 value on B is inverted and becomes a 1 on the input to this AND gate. So there is a brief period of time, exactly as long as the propagation delay of this inverter, where my output's actually low. And it's only when after the B signal sort of has been inverted and it's on this AND gate that my output sort of goes back high again. Right? So that's called a glitch, right? Because the output should have gone from a 1 to a 1, right? You can see here the output's 1 when for the final values of A, B, and C, it should still be a 1. But it glitched right in the middle. The output became low just briefly because of the propagation delay of this inverter. And you can see on the KMAP that that's reflected by the fact that I sort of move from one circle to another. And kind of the rule of thumb is that anytime on my KMAP I sort of leave one circle and go to another, I have the possibility of a glitch. So this circuit's not going to work, right? This is the same problem as like that switch bounce driving our clock input. Like we have an inadvertently fast signal that we don't want our circuit to respond to, but the clock input on the D flip-flop is clearly going to respond to this. So to solve this problem, we got basically two strategies. Number one, I can remove the glitch. So it's a little redundant, but I can add an extra term here, this not AC term, that overlaps these two circles. That not AC term would go right here around this box and this box. And what that means is that even though I'm leaving, like in this case, the purple circle and transitioning to the orange circle, I would stay within a circle that enveloped these two ones, and so there would be no glitch. All right. So number one, I can add terms basically to kind of overlap that transition to remove the glitch. My other strategy is that I can sort of buffer the signal, so I can take the output of my my logic, combinational logic, and I can send that to a D flip flop run by a clock that is slower than my glitch signal. And so there'd be like effectively that would be right here, right? There'd be another little flip flop in between my combination logic and my clock signal. And by doing that, right, if this clock is slower than my glitch, then I'm effectively sampling my combination logic output Y at a slow enough frequency that that it's exceedingly unlikely to sort of capture that glitch signal. That as long as this clock is slower than this glitch here, I'm most likely to sort of capture Y maybe right here, like on a rising clock edge, and then maybe not till much later on another rising clock edge when the value of Y has settled. So I can sort of buffer the signal in that way. All right. Okay, so we talked about the way glitches can affect combinational logic circuits and how it really matters to us when we're connected to something that responds quickly. So here, like a D flip-flop we saw on the last page, of course, if we're connected to a microcontroller that responds really quickly, or a finite state machine that responds really quickly, then we'd have similar problems, which we could solve by either adding terms to remove the glitch or buffering the signal with a little D flip-flop. The last circuit we're going to look at is the finite state machine. All right. So here's the block diagram for my finite state machine, and what we're going to look at is a little waveform here that represents a single sort of transition in my state machine. So you notice right here, when the clock goes from a low to a high, that's point A, there is some amount of delay before the output of my D flip-flops here reflect the new values, right? So there's a propagation delay associated with my D flip-flops, just like with any of my other combinational logic. So there's some delay there, right? That value is going to wrap around here into my combinational logic block, which is figuring out what my next state is going to be. So that signal, then there's that shows sort of that's the B signal here, like where this is present on the combinational logic block here. Just like we saw before, right? There's some propagation delay associated with all of these gates. Okay, so there's another propagation delay here from B to C before Q prime takes on the correct next value, right? So this is like the actual next state that I want to go into my D flip-flops. And then lastly, don't forget that for our D flip-flops, we have this setup time. So, oops, sorry, this is on the falling clock edge. I should show this on the rising edge, so forgive me there. But so whenever, let's assume this is a rising clock edge, right? On the next rising clock edge, there's some amount of time, the setup time, prior to which my Q prime has to be stable. Otherwise, I put my flip-flop into an unknown state, right? And so what this does is puts a restriction on how fast that clock can be. In other words, how small that the period of that clock can be, right? So you can imagine that if we were to try to take this waveform here, kind of squish it as much as we could, we have to make sure that the full clock cycle is large enough to handle one propagation delay from the D flip-flops, another propagation delay from our combinational logic, and still meet the setup time. So the equation for that is here, right? The period of our clock has to be greater than the propagation delay from the D flip-flop, the propagation delay from the combinational logic block, and our setup time. And so based on these values, we have a maximum frequency that we can use for any of our finite state machines. And for most of the finite state machines we're designing, it's probably obscenely large because these propagation delays and setup times are relatively small, on the order of tens of nanoseconds. But you may find yourself designing finite state machines where you want a really fast clock, and you should know that this is sort of an upper limit. All right. So there we go. That's our lesson on time parameters, right? We started with 3 revelations about the fact that circuits behave kind of non-ideally, right? Signals take some amount of time to transition. There's a propagation delay associated with each of our logic gates, and our clock signals need some sort of setup and hold time around which the inputs need to be stable. Otherwise, weird stuff happens to the flip-flop. And we showed you a number of ways to sort of handle that in circuits, right? So we started with this idea of switch bounce and how this is, a slight diversion into fast signals. And if we're driving something that responds quickly, we need to address it. We looked at a couple of hardware and software ways to address switch bounce. And then we looked at 2 other circuits where propagation delays and setup times affect our the operation of our circuit, right? And in particular, if I've got combinational logic that is susceptible to a glitch, then I need to either remove that glitch by adding terms to my K-map or buffering the signal. And for my finite state machines, when I account for my propagation delays and my setup times, I realize that there's a maximum clock frequency for a given finite state machine that I'm allowed to run it at. Otherwise, I'm going to potentially violate this setup time and cause my finite state machine to do weird stuff. All right, that's all I got, folks. Have a great one.